In this section, we will continue with the time domain, stability. Okay? Stability in time domain. Stability in time domain is analyzed with the state space form. Okay? Have you heard of the state space, Hakan? Durumzai. Yes. And so it's like this one, 0, 1, minus 2, minus 1, minus 2, and plus x and b times u, right? And so, why we need to use the state space form? Remember me. Just remember me, right? So, tell me. Why do we need to use the state space instead of transfer function? We can define the what, the NTH order system based on this formula, right? In the transfer function, we have the one input and one output, right? But in the state space, we can select, for example, 2 input, 4 output. This is the huge advantage for the what, for our nomination or the designing the R system dynamic equation, okay? And so, we need to learn about it. And so, it's directly related to what, the matrix equation, right? For example, we have the bigger A in here with the coefficients of the A, B, C, and D. This can be converted into the what? The transfer function. And so each transfer function has a common characteristic equation. But we can analyze this system in order to what? In order to get the system is stable or not, to what? To check the eigenvalues of this system. What is eigenvalue? What's your name? What's your name? Furkan. Furkan, what is eigenvalue in matrix? Eigen means that unique, okay? Eigen. It's only one value, eigen, and its value. And so eigenvalue are considered as the specific number to define the system in matrix domain. For example, we have the transfer function in here, TS, just like this one, 5, S plus 5, S plus 2. And so we have 2 roots in here, right? But these 2 roots, minus 5 and minus 2, is the what? Is the eigenvalues of this system. Because it's a unique. It defines to the system. Okay? And so, just remember that in the linear algebra, we can check the eigenvalue. Or we can find the eigenvalues with this domain, right? Have you remembered that? This form, A times X is equal to what? Lambda times X. Lambda is equal to what? The R eigenvalues, right? In the linear algebra, you studied it, right? And so, in order to find out the eigenvalues of these terms, we need to write this equation with this domain. Lambda x minus ax is equal to 0. And so x are common parts of this equation. And then lambda I minus a times s x, which is equal to 0. Just remember the differential equation. If we find out the solution of any differential equation based on the 0, this gives us the homogeneous part of the differential equation. Or in this lesson we will call it to what, Furkan? Special values, but we call it the natural response of these terms, because if we have these two roots are indicating to the natural response, and so these eigenvalues must be contained with these natural roots or the response of these terms. Or in differential equation, if we have the special form of solution or the homogeneous form of solution, and then we will focus on the homogeneous form, which we call it in this lesson to what? Natural response or the natural solution, which is equal to the what? The eigenvalues. Okay? And so this x can be written as to what? Lambda I minus a over minus 3 times 0. This is the basic solution for the output of these equations. Okay? And so this x can be written as, just remember the linear algebra theory, adjoint equation lambda I minus a and determinant of the lambda I minus a times 0. Okay? This is the solution of our time response for this study. This is equal to 0, but if we have any initial condition and then this value replaced with with the initial condition. Okay? Because in this case we don't have any actual output or any actual input values in here. Just the system is given in here. Normally we have the state space just like this one, ax plus bu, but in order to check the stability in the state space domain, we just look only the a value in here, because the u is a controlled variable. Okay? And so x dot is equal to the ax are the basic solution for the stability in the time domain. Okay? And so this adjoint equation is equal to the numerator of the transfer function. This determinant of this term is the denominator of the transfer function, right? It's equal to this one. And so this form directly turns into the into the transfer function. Or we can convert the transfer function into the state space domain, right? And so this is also equal to the characteristic equation, right? It must be. Okay. And so our basic condition is that if we have any state space, and so this lambda should be replaced with the s I minus must be equal to 0. This gives us to characteristic equation. Okay? Why we replace with the lambda with the s in here? Just tell me. Why? Yes, in the transfer function domain we have the s, but in time domain we have a unique values for equals to the the eigenvalue, right? And so this eigenvalue is converted into the s or roots of the transfer function in Laplace domain. Okay, these two terms are identical to represent to the natural response of our system. Okay. And so how can I prove that? So we can define the example of this mass spring damper system in here, just like this one. Okay, m, f, x, k, and c. Okay, and so the equation of motion of this equation is in here, just like this one. F is equal to the m x dot dot plus c x dot plus k x, right? This is the general solution of this term. And so in S domain, we have the fs s square xs plus cs xs plus k xs, right? And so the transfer function can be written as the xs divided by fs is equal to the what? 1 divided by ms square plus cs plus k, right? This is the transfer function of this mass spring damper system, right? Or in state space form, we have the arbitrary number or the variable z1 is equal to the what? The x, z2 is equal to the x dot, right? And so z1 dot is equal to the what? z2, and z2 dot is equal to the what? X dot dot, right? And so minus k divided by m times z1 minus c divided by m z2 plus f divided by m, which is given in here. Okay, so our state space form is equal to the what? The x dot dot, which is equal to the what? 0 and 1, and minus k divided by m minus c divided by m, and x dot plus 0 1 divided by m f, right? This is the state space form of this term. But in order to analyze the time domain stability, we just look only to what? This term, because the f are the outside parameters, the external input values, and so this cannot be included in the stability form, because if we select a different f value, we can make the system stable, right? And so the natural response is only related to the what? This term. Okay? And so, for example, m is equal to the 1, c is equal to the 3, and k is equal to the 2. Okay? We can select it just like this one. And so the RA matrices becomes to what? 0, 1, and minus 2 and minus 3. Okay? And also we have the xs and fs value is equal to the what? 1 divided by s square plus 3s plus 2. Okay? See the analogy of this term? In this form, in the canonical form or fuzz variable form, we just have the what? The roots value in here, right? This is the system coefficients at this place. And so, how can we check the eigenvalues of this term in this domain? Can you close the door, please? Yes. And so, in order to calculate the determinant Si minus A, which is equal to 0, can be yield to the what? The characteristic equation in here. And so, how can we do that? In the first place, we have the S times I is a I matrix, which means that we have only diagonal elements in here, just like this one, and minus we have the A value in here, just like this one, minus 2, minus 3, and which is equal to the what? The S multiplied with a scalar value in here, just like this one. And so this is the first time, it's the S, and it's the minus 1, and after that this 2, and this is the what? The S plus 3, because we have the negative value and also this is the negative value. And so how can we find the determinant of this term? Yes, we multiply this term and this term which is in here, and so that Si minus A is equal to the what? S times S3 minus 1, 2, which is equal to the what? The S square 3S plus 2, right? The determinant of this matrix in the eigenvalue form, which is equal to the what? The denominator of our system, right? See the analogy in here? XS and Fs can be given with the what? The 1 divided by S square 3S plus 2, and so this is directly equal to the what? The each other, right? And so how can I check this stability? S plus 2, S plus 1 is equal to 0, and so S1 and 2 smaller than 0, and then we can say that the system is stable, right? This is simple. In the MATLAB application or in the MATLAB program, we can check the R state space matrix A or B in order to what? In order to get the values of the eigen, right? And so the eigenvalue S1 and 2 must be equal to 0. Also lambda 1 and 2 must be smaller than 0, right? This is related to what? The frequency domain. This is related to what? The time domain, right? If these conditions are supported or provided from our system, and so the R system can be considered as the stable, okay? In control theory, we will try to what? To stabilize the R system based on the what? The PID controller, or the selecting the different coefficients, just like the K, just like the derivative coefficients or the integral coefficients, based on this information. But at the end of this design, we will focus on only to what? To stabilize the R system based on this information, okay? And then we will drive the system to the specific point, because if our system is stable, for example xt, and so if we know this system goes to this one, for example this is equal to the 10, okay? This system is stable, right? And so how about if we select the k is equal to the 1 divided by 10? And so this is the GS response. And so if we select the 1 divided by 10, these coefficients affect the system just like this one. And so we can decrease the values of the what? The final value. Yes, because the system at the end of the time, or the time is going to the infinity, and then the system going to somewhere, any constant, 10, 5, 4, okay? And so if we have this condition, and then we will drive the system to the specific points based on this information. But we cannot drive the system just like this one, because it goes to the infinity value, right? Actually we can control this system, but this system cannot be scaled, because at the time is increased, and then we will get the what? The boundedness values, or the higher value at this time. But the other terms is equal to the what? The constant value, bounded value. This is the unbounded, and this is the bounded, right? this system can be tracked at any reference, but this cannot. Okay?
So how do you like the system? How do you use the second system?
The second system, for example, this is equals to the what, for example, gs is equal to 5 divided by s minus 5. Okay? And so what's the solution of this system? In the gt response is equal to that 5 exponential over 5t, right? This is the solution of this system. And so t is grow, and then this is also grow. So how can we design this system? In the PID controller design, if we select the CS, for example, s minus 5, and so these two terms creates the what, the TS, G times C, which is equal to what, 5, S minus 5, S minus 5, and so this is equal to what, to 5. And so we can control this system based on this information. This is the main purpose of the what, designing the controller for a given system dynamic equation, or the state space form, or the transfer function form. Okay? And so, do you understand the basic difference between the time and frequency domain in here? And so, if we want to track any reference point or the desired point, and then we must first to what, stabilize our system based on using the proportional coefficients or the derivative coefficients, or some other implementation of the controller design, which is conditioned to what? Just only equation, either which is given in the what, the frequency domain or the time domain. It doesn't matter, right? Any question? Okay. And so we have two stability rule in here, frequency domain and the time domain. In the time domain, we should always check what the eigenvalues of this term, which must be smaller than the 0. And so in the transfer function domain, we should check the root of the R transfer function in the denominator, which is equal to the characteristic equation, and then all the roots should be placed at the what, left hand side, which means that must be smaller than 0. And so we have one more stability rule or the method for the linear system or the nonlinear system, which is called the energy approach. Okay? So, for example, if we have system just like this one, x1 dot is equal to minus a x1, and so if the a1 is greater than 0, we can say that the system is stable or not. Hakan? Not. Why? Huh? Yes, and the a1 is positive, and so we have a negative term in here. Okay, and so this yields to the what? The stable system. And so everything in this system is calling the states, right? And so each state has own internal energy in a square form. Okay, and so how can I define the arbitrary energy function for this system? We can call it the Lyapunov function. Have you heard of it? If you want to design or define the energy form of these terms, we can select the arbitrary function, which must be positive, x1 square, just like this one. Okay, this is the state energy form in this domain. If we take the square form of this term, which is a signal, just remember the Parseval theorem, we can define the energy form of a signal or the physical entity based on this information. Okay, and so this is, or this must be always positive because it's energy. Okay, and so also including the dynamic states. For example, if we have the x2 value in here, and then we should add the another energy term in here, 1 divided by 2 times x2 square form in here. So is this the energy? What is the final value or the smallest value of this term in here? What's the smallest values for this L function? 0. Why? Because it's a square form, right? And so it cannot be negative, right? Just like the energy in the real life, right? And so if we have a condition for the stability rule, and then we want to act like this system, just like this one, when the t is going to what? Infinity value. And so this L function is going to what? To the 0. And so this x1 is going to 0, right? This is our condition, right? And so how can we do that? If we know this term, and so we can check the derivative of this term because it's the energy form dynamics. Okay, and then L dot is equal to the what? 2 times 1 divided by 2 times x1 dot x1 dot.
Saat 2'deki etkinlikten haberiniz var mı diye söyleyecektim.
Yok.
Tamam, saat 2'de bir konuşmacımız gelecek de dışarıda birçok bekleyen var, sadece haber etmek istedim.
Tamam.
İyi dersler dilerim.
Evet.
İnanın bilmiyorum, yani uzun sürecek ama.
Okay. And so this L dot is equal to what? 1 divided by 2, and so x1 dot x1 dot. Okay, and so this must be replaced with what? The x1 dot times, we have x1 equation in here just like this one, a times x1, and so this yields to what? A times x1 square, right? And so this function is equals to the what? L dot, this always positive, this negative, and then it's going to just like this one. And so we can say that if the L dot always or equal to the L dot 0 and L positive, and then the R system can be stated as stable. Okay, we can say that, right? Because the proof of this theorem can be accomplished by using this form. Okay, do you understand what I'm saying in here? Just using the geometry of this term, and so L, if the always positive, and then L dot is the negative or equal to 0, and then it always goes to what? To 0, right? This is called the energy approach for the R system notation. Okay.